class today, you will need science notebook and your Unit 10 packet, which you picked up on Friday, Unit 10 packet. And in your Unit 10 packet, you should already have your algebra paper done. We did this in class, and we are going to be working on Boyle's law and this next page, Charles' law. So you want your packet and you want your science notebook. So I'm going to be writing notes on the board. I expect you to be writing those same notes in your science notebook with me. We're going to do some investigations looking at LabQuest data, working with some sensors and seeing mathematically how some variables are related. So let's just go ahead and write down like our objective. So our objective, the objective for today, our learning objective is to describe the behavior of gases by observing the relationships between measurable variables. So we're describing the behavior of a gas by observing the relationship between measurable variables. So if I have a balloon full of a gas like oxygen, or I have a balloon full of a gas like nitrogen, or I have a balloon full of carbon dioxide, and I ask what variables can I measure about this volume of gas? I can measure the volume, I can measure the pressure, I can measure the temperature, I can measure the amount of gas. This would be the moles of gas, so this is moles. Volume, pressure, temperature, amount, and I could also measure type. Technically, I can measure the type of the gas. Like I could identify that. I could say this is oxygen versus nitrogen versus carbon dioxide versus a balloon full of, methane gas, or I suppose I could have a balloon full of, hydrogen gas or propane, right? There are a whole bunch of different gases that I could investigate. Some of these gases are nonpolar bonds making nonpolar substances, nonpolar bond, nonpolar substance, while others are polar bond, nonpolar substance because of symmetry, but they all share in common that they are gases. So we need to start by making some assumptions about how gases behave. So we're going to write these. These are going to be important variables. So join me over here. We'll scoot the board over. Some assumptions. Assumptions about gas behavior. And these assumptions about gas behavior have been developed based off of observations of lots and lots of data. So the first assumption that we make is that the forces acting between these molecules are very, very weak. So gas molecules have weak intermolecular attraction. So much so that these gases have weak intermolecular attractions, and these interactions are so weak, we say that they don't even interact. So we rephrase this and we say that gas molecules do not interact with each other. Gas molecules do not interact with each other, okay? That's statement number one. I'm going to slide you guys over here. And perhaps it'll be a little bit easier to see what I'm writing on the board. So gas molecules have weak intermolecular attractions because they are nonpolar bond, nonpolar substance, or polar bond, nonpolar substances. So because of this statement, which we made when we talked about intermolecular forces at the end of chapter or unit 9, we can make this statement: gas molecules do not interact with each other. Statement number 2, if they collide, we assume those collisions are elastic. So if a gas molecule collides with something, that something could be another gas molecule, it could be, in my balloon of science, it could be that this gas molecule is going bing, bing, colliding with the wall of the balloon. I assume that's elastic. It hasn't lost any of its energy. I also assume that if these two have collided with each other for some reason, bing, bing, like this, that they will, in turn, have elastic collisions. If gas molecules collide with each other or a wall, with something, the collision is elastic. Nothing happens. Like, it doesn't lose any energy. It just goes bing, 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 just collides, and it keeps moving. All right, and the very last assumption that we make about gas molecules. Okay, they've got weak bonds. They don't interact with each other. If they do interact with each other, we assume that they just go like boing, boing, and they bounce off, and they don't do anything to each other. And then, heads up, there are 4 statements. We're on number 3. The third one states that gas molecules are weak. Gas molecules collide, and the collision is elastic. That their size. We also make the statement that gas molecules are tiny. They're tiny. Their volume is tiny. Gas molecules are tiny compared to volumes that we work with. Boom, like this volume of space right here. The gas molecules are tiny compared to volume of study, that they don't actually occupy any space that we care about. So gas molecules are tiny compared to the volume of study. So when we talk about the volume of the container, we don't care that the gas molecules technically occupy part of that volume. We just talk about the volume of the container. So gas molecules are tiny compared to the volume of study. So we're not really concerned about that. Right? We just acknowledge that they're tiny. And then the last thing is, it doesn't matter what type of gas we're working with. All gases behave the same. All gas molecules, spelled it wrong. Try that again. Molecules, all gas molecules behave the same. We'll polish that idea. We'll polish it just a tiny bit. But for the most part, what I'm talking about is when a gas is behaving perfectly, ideally, when everything is happening the way it's supposed to, we find out that they don't interact with each other. If they do interact with each other, it's elastic, that they're tiny compared to the area that they occupy, and that all gas molecules behave the same way. And we say that this is ideal gas behavior. So these statements are called ideal gas behavior. Ideal. Ideal gas behavior. Okay, so does this really happen on the surface of the Earth? It can. Does it happen always? No, but for our purposes, when we're talking about just perfect relationships between things, we're going to assume that these 4 statements hold true. That gas molecules don't interact with each other, that they are, if they collide, it's elastic collisions, meaning they just bounce off and keep going, and that the gas molecules are tiny compared to the volume they occupy, and that all gas molecules will behave the same way. So if I give you a question and I ask, what's going to happen to the oxygen molecules within this system. And then I ask another question that talks about what happens to the nitrogen molecules. You don't really care that I changed the gas because the gases all behave the same way. So what we are studying doesn't matter. All that matters is that it's a gas. So our first person that we're going to talk about, the first individual who is really doing research on gases that we credit is Boyle. So Boyle will be our first person. So let's head to our science notebooks. And I'm going to pull you back over here. Okay, so in our science notebook, we are going to write down Boyle. And I'm going to zoom you in a little bit so you can see what I'm writing. Okay, so we are talking about the behavior of gases, and the first person that we are investigating is Boyle, B-O-Y-L-E. And Boyle was interested in the relationship between pressure and volume. And what he did was he was investigating different types of gases, looking at initial systems, system 1, balloon number 1. And then he would modify one of these two variables and observe what would happen to system 2, the after. So we can call these system 1 and system 2 like pressure 1, volume 1, pressure 2, volume 2, like this. We can also use initial and final, initial system and final system. Both of those are fine. They are asking the same thing. In your periodic table, you're going to see that we use the 1s and 2s to indicate the initial and the final setup. So let's investigate the relationship between pressure and volume. And so to help us do that, I've grabbed my LabQuest and I have grabbed a gas pressure sensor because we're investigating the pressure of gases. All right, so I'm going to slide this out and bring my LabQuest. I'm going to slide the LabQuest over and get it to change its orientation. Okay, so here's my LabQuest and I have my pressure kit. So here's the sensor itself, the gas pressure sensor. I'm going to zoom out just a touch so you can see this a little bit better. And what I have here is a syringe system. Okay, so I have a syringe, and I will be able to connect the syringe directly to this sensor. So the syringe has different volumes initially, and I can adjust it just by changing the syringe's placement. And this will twist onto the side of my gas pressure sensor. And I'm going to connect the sensor to my digital output. Oh, my bad. Guess it's one of these. There we go. If at first you don't succeed, change your location you're trying to attach it to. Right, rotate. Okay. So it has rotated. All right, and we see that the sensor is measuring in the standard unit of pressure, which is kilopascals, and that is the SI unit. So let's see if we can't get the screen to lock so it stops adjusting. All right. Okay. So what I'm going to do is I'm going to choose different volumes. Actually, the easiest way to visualize how this changes over time is graph it. So we're just going to graph it. We're going to ask what happens to the pressure if I change the volume. So in our science notebook, we're writing down what will happen to pressure. What will happen to the pressure from a gas if the volume of The volume the gas occupies? Yeah, that sounds the best. What will happen to the pressure from a gas if the volume the gas occupies changes? Okay, so we just take a second here. Upside down. Okay. Ah, so close. Okay. So in your notebook, you wrote down what will happen to the pressure from a gas. So inside of here, gas particles. What will happen to the pressure that those gas particles will exert if I change the volume that they are allowed to occupy? So in your science notebook, make a prediction. Our options would be the pressure will increase, the pressure will decrease, or the pressure will stay the same. So it's not about being right, it's about guessing. This is where you're making a guess. All right. So the pressure will increase, decrease, or stay the same. And you just have to pick one. All right, so I have my screen, my lab quest of science. I have my gas pressure. I'm going to start with the volume being the maximum volume I can measure on this cylinder, which is 20 milliliters. I'm going to attach it to my gas pressure sensor. On my lab quest, I'm going to say start collecting data, and I'm going to press the start button to tell it to start collecting data. And you will see that there's a little dot. So now I'm going to depress the plunger. And that is as far as I can make it go. Okay. Boom. Here we go. Let's look. This is where it was just setting on the counter and I didn't do anything. And here I decreased the volume, and as the volume got smaller, the pressure increased. All right, so we look at our science notebook. As volume decreased, pressure increased. So if one goes up and one goes down, like this, one goes up, one goes down. As volume goes down, pressure goes up. So they're not directly related to each other. If they're directly related, then as one went down, the other one should have gone down. They're doing the opposite of each other. So we say these are inversely related. If I think about this mathematically, if they're directly related, as volume increased, pressure would increase. So this isn't what they're doing. As they must be opposite each other. So if volume increased, pressure, so they must be on the same side of the equal sign. So let's just try this. If they're on the same side of the equal sign, are they inversely related? Well, they would have to both equal the same number. So let's pretend like they equal 10. So if volume was 1, then pressure is 10 and we equal 10. Okay, but if volume increases to 2 and we still can only equal 10, then pressure must be equal to 5. So as this one's going up, this one's going down. Okay, so if this one's 5, then this one becomes 2 to keep it equal to 10. And if this one is 10, pressure becomes 1 to keep it equal to 10. So I notice that when they're on the same side of the equal sign, they are inversely related. As one is increasing, the other is decreasing in magnitude. So all of Boyle's work was to mathematically and experimentally give evidence that it didn't matter. It doesn't matter the type of gas that, oh good Lord, my handwriting is horrible today. It doesn't matter the type of gas. All behave like this. All gases follow this pattern. All gas molecules follow Boyle's law. So it doesn't matter the type of gas. All gas molecules are following Boyle's law. And Boyle's law is the relationship between the pressure and the volume, boom, boom, pressure and the volume of a gas. And we found that they were inversely related. So let's, if you need to at any point, of course, pause the video, write down what you need to write down, and then come back and join us. So we're going to go to your science notebook, or excuse me, to your Unit 10 packet. I'm on the Boyle's Law worksheet page. I'm going to zoom in just a touch. So this is Monday's lesson, and we're doing it together in class. And these are just a recap of our notes. Boyle's Law. So which pair involves variables that are inversely proportional? In other words, what did Boyle study? Boyle studied pressure and volume. Okay. Draw a line on the graph provided showing the relationship described by Boyle's Law. Okay, well, Boyle's Law was pressure and volume. So we have to put pressure on one axis, pressure and volume. And let's think about what those words meant. As the pressure in my syringe, as I looked at this syringe, right, my volume, as my volume decreased, my pressure increased. As my volume decreased, my pressure increased. Okay, so if we think about what that's going to be like, as my volume decreased, so here's like large volume values, right? As my volume decreased, my pressure increased. So if I draw a line on the graph showing this relationship, it would look like this. I have high pressure at small volumes, high pressure at small volumes. I have low pressure at large volumes, and they are oppositely related, which is why it is decreasing. Negative slope means inverse relationship. As one increased, the other is decreased. As one increased, the other decreased. Boyle's law states that when blank and blank of a sample of gas are held constant, oh, timeout, what did we assume was the same? Well, on the board earlier, we wrote that we could modify volume, pressure, amount, and temperature. So Boyle's law states that when the amount of gas and the temperature of a sample of gas are held constant, its blank is blank proportional to the O. Okay, so its pressure is inversely proportional to the volume. I could also write the volume is inversely proportional to the pressure. Like both of those statements are true. Okay, so let's look at an example of applying this system. So I have an example number 4. A balloon filled with helium. Occupies a volume. Okay, so I've got a volume of this at 752 torr. Ooh, hey, that's one of those funky labels for pressure. That's a pressure. And 25 degrees Celsius. Okay. What will the volume be, oh, I want this, of the balloon at a pressure if there is no change in temperature? Okay, there's no change in temperature. No change in temperature. So I'm just going to cross out the temperature value because I don't care about it. Nothing's changing. So I see that I have volume and pressure, volume and pressure. So the very first thing I do is I make a variable list. I have volume and pressure, V1, P1, volume and pressure, V2, P2. I have an initial 1 and a final 2. So let's write down the information. So I wrote the variable list. Now let's write down the variable values. So I have a volume 1, V1 equals 1.50 liters, and a pressure equals 752 torr. Okay. What will the volume? Oh, hey, I'm looking for volume. Volume equals question mark. And the pressure be of 438 torr. Okay. Equals All right, V1, P1, V2, P2. I am going to need some relationship. I don't know all of these other variables, but I can use a proportion. That's a math trick. I can set an initial equal to a final. So I found that mathematically, these guys belong on the same side of the equation sign. See, right down here? They belong on the same side of the equal sign. So my equation is V1, P1, or it's usually written the other one way around. Okay. P1, V1 equals P2, V2. That is the equation I'm going to use. This is on the back of your periodic table. You can look it up on the back of your periodic table. I solve my equation in variable form. I solve for V2. Okay, I'm looking for V2. I solve the equation for V2. So I divide by P2, currently multiplied, dividing is opposite. Divide by P2. I write the equation in letter form. And now that I have it in letter form, I substituted my values. And all I need to check is that the units are the same. Pressures in torrs, pressures in torrs. Good. Volume is in liter. My answer will be in liters. So I substitute in pressure 1, 752 torr. Volume 1, 1.50 liters, divided by 438 torr. Torrs cancel. I grab my calculator, which I don't have. I grab my calculator, solve my answer, and I will want three significant figures in my answer. Woohoo! Calculator of science. I found it. Okay. Hopefully you brought your calculator to class as well. 752 times 1.5 equals, divided by 438. Three significant figures. Three significant figures. Keep the 2, keep the 5, keep the 7. Round the 7, 2, and 8. 2.58 liters. Box your answer. Ta-da! That's it. Your job is to finish. Finish these on your own and check your work. Check your work with your table partner, and you can check your work against my answers. My answers are on Schoology under Boyle's Law problems solved. Ba-dum-bum-ching. All right, fantastic. So solve those. That is your homework. You can do it now, or you can do it when we are done talking about Charles' Law. That is your decision. Okay, so let's move on to Charles' Law. And I'm going to go back to my science notebook. So in my science notebook, I'm on my next page, and I'm writing down Charles' Law. Charles's Law, as within a possessive apostrophe. So recall again that gases can be described by measuring their volume, their pressure, the amount of gas present, and the temperature of the gas that is present. When we're measuring temperature of a gas, what we're measuring is the average kinetic energy, the kinetic energy of the gas particles inside of the gas substance. So usually we're analyzing a specific amount by creating a volume of gas that those particles occupy. So we're going to look at some initial system, and then we're going to modify this system. And in the case of Charles, what he was interested in was what would happen if we changed temperature. So if we change the temperature of the gas, what will happen then to the other properties that we could see? So we're going to, of course, keep the amount of gas the same. If that would make sense. We aren't opening up the container. We're keeping the amount the same. We're keeping the type of gas the same, but we're behaving ideally, so it shouldn't matter what type of gas that we are using. We are going to observe how the volume how the volume is going to change. So I have some initial system and then I have some final system, and I want to know how the volume changes. So if the volume is changing, then I would assume that the space that this gas occupies is going to increase, or the space that this gas is going to occupy is going to decrease. So that's what Charles was interested in being able to mathematically describe, but based off of studying a whole bunch of different types of gases and changing their systems. So what will happen to the volume of a gas if the temperature, which we said is just a measurement of how fast they're moving, if the temperature of the gas changes. All right, what will happen to the volume of a gas if the temperature of the gas changes? All right, so we wrote that down, and I'm going to do an investigation. We're not doing these as independent labs. I feel like you may intuitively have a pretty good feel for what's happening here. So I'm going to flip the camera around and have you join me over here. Hello, close-up, my close-up moment. And I have a Bunsen burner of science and a beaker, or excuse me, an Erlenmeyer flask with some water inside of it. Water, which we assume above the water being a polar substance, there is water vapor above it. So we have gas, water, and then just room temperature water. So here's my beaker of room temperature water. So Charles was interested in understanding what would happen to the volume that a gas occupied. So currently the balloon is not inflated, and so we're going to say that the volume of gas that's occupied is just the volume inside of the Erlenmeyer flask. If the volume increases, then the gas will attempt to escape the Erlenmeyer flask and inflate the balloon in some way. If the volume of the gas decreases, then it will take up less space than the volume of the flask, which we would see as the balloon actually depressing and going inside the Erlenmeyer flask. So I will heat up the gas molecules by adding heat to the system. So we see the gas molecules are attempting to leave the system. So, oh, there we go. The trick is to do this without breaking the balloon. Okay, and then what will happen if we decrease? So increasing the temperature, increase the volume. What will decreasing the temperature do? So decreasing the temperature, and then you can actually see the balloon is actually sucking down inside of that. There we go. All right, so decreasing temperature, decreasing temperature, decreased the same volume of a gas. So we haven't changed the amount of gas, so the amount has not been changed. The pressure that's exerted on this flask and on this balloon, that hasn't changed. All we changed was temperature, and then we inferred what happened to volume. So Charles's law, which was, oh, look at, where's my goggles? Where are my goggles? Charles's law is looking at temperature and volume. So let's go back to our science. Okay, so what happened to the volume of the gas if the temperature of the gas changed? So if temperature increased, volume of the gas increased. If temperature decreased, then the volume decreased. We would say that because one increased caused an increased, or a decreased caused a decreased, that these are directly related or directly proportional. Yeah, directly proportional. If I think of this mathematically, I'm going to have my variable temperature and my variable volume. on opposite sides of an equal sign. So that if one increases, so if temperature is 1, volume is 1. If temperature is 2, volume is 2. If temperature is 3, volume is 3. If temperature is 4, volume is 4. If they're on opposite sides of the equal sign, I can show this direct relationship. If I had to put them onto the same side of the equal sign, I would need to divide one by the other. See how they would have to be one on top of the other in order to have them on the same side of an equal sign. And then they would need to be equal to something. So either they're part of a larger equation, and this is some other variables, or it's some initial and some final system. So we have to have some initial system and some final system where we've got 1s on this side and 2s on this side. So let's grab your periodic table. All right. On the back of your periodic table, there is a box that is labeled gases, and inside of here we see Boyle's and Charles stated pressure volume equals some pressure final, some volume final, or PV equals P1V1 equals P2V2. Note, they don't have ones here. That's fine. Totally don't care. As long as you know that these variables are from one system, some initial, and these variables are from some final. Here we see Charles's law. Volume and temperature are directly proportional. This is not a problem. The V's on top, the T's on bottom, rock on. I wrote it the other way around, but that's totally okay. See, if I had this T equals V and I'd solved it the other way, I'd have V on top and T on the bottom. Okay. So let's state Charles's law. Charles's law states that some initial volume will be equal to some final volume with respect to temperature. P initial and final. Okay, my pencil was running out of lead there for a second. Final. Okay. You don't have to memorize these equations. These equations are on the back of your periodic table. You will always have this periodic table. So understand the relationship, but don't worry about memorizing that. It's not going to be required. So let's look at your packet. We go to the Charles Law handout. Which pair involves variables that are directly proportional? Hey, that's what we just studied. Charles studied temperature and volume. We did the balloon. This was the volume of the balloon. This was the Bunsen burner. So we're talking temperature and volume. So let's put temperature on the y-axis, volume on the x-axis. As the temperature increased in magnitude, the volume of the balloon also increased. If the volume decreased, the temperature decreased. Okay, so if we're sketching this, as the volume increased, the temperature goes up. So it must be a linear relationship where they are directly related. So directly related, that is the positive slope of the line. Okay. As temperature increases, volume increases. If I write this graph as a sentence, I would say as temp of a gas increases, the volume of a gas also increases. That's what this graph tells me as a scientist. Let's continue. Charles' law states that when the blank and the blank of a gas are held constant. Okay, what didn't we change? Well, we could change volume. We could change pressure. We could change amount, and we could change temperature. In this experiment, we changed temperature, we observed volume, so we didn't change those. Charles' law states that when the pressure and the amount of a gas are held constant, the blank of the gas is proportional to, okay, so then the volume of the gas is directly proportional to its temperature. And we could say The temperature of a gas is directly proportional to its volume. That'd still be a correct sentence. All right. When we work with this in an equation setting, there are other variables in the system that we're not using, so the only way we can use Charles' law is as a proportion where we have some initial and some final. So we have some initial, volume over temperature equals some final, volume over temperature. So let's apply this law and look at a system and solve a problem. A sample of air has a volume of 2.25 decimeters cubed when its temperature is 298 degrees Kelvin. If the temperature is increased to 373 degrees Kelvin without changing the pressure, okay, what is the new volume? So they gave me a volume right here, and they gave me a temperature, right? And we have a new temperature, and they want me to say what's the new volume. So this is just an application of Charles's law. Step 1, variable list. V1, T1, V2, T2. I always identify the V1, T1 as the first information that they gave me. So they told me a volume of 2.25 cubic decimeters. Okay. 2.25 cubic decimeters. They gave me the temperature for this volume as 298 Kelvin. 298 Kelvin. If we increase temperature, I have a new temp, so the new temp is 373 to 373 Kelvin, then what's the new volume? Volume is what I'm looking for. If we look at our units, okay, so we made our variable list. If we look at our units, they gave us cubic decimeters. We never use cubic decimeters. They're on my periodic table. Sure, they're right here. 1,000 milliliters is 1,000 cubic centimeters, which is 1 liter, which is the same as 1 cubic decimeter. Okay, so congratulations, worksheet. You can give me units I've never seen before. I shouldn't be intimidated. I see here that a decimeter cubed just is a liter. All right, good deal. But more importantly, I don't care. As long as I know that that's what my label has to be in the end, and the labels are the same on both sides, I can use any unit that they give me. So I'm not even going to bother changing it. I'm just going to use it because it doesn't matter. If they didn't tell me the unit, I have to report volume, and I'll just tell them the volume in cubic decimeters. So the first thing I do is I write my equation in variable form. So I've got V1, T1 equals V2, T2. If you don't want to write the ones, that's fine. I was taught with ones, I end up writing ones. I'm looking for V2, so you can solve this equation lots of different ways. I see that it's on the right side. It's already on the top. The easiest way is just to get it by itself. So I have to do two things when solving for an unknown. One, it has to be on the top of this fraction. Two, it has to be by itself. So I'm just going to multiply by T2. What I do to one side, I have to do to the other side. Those cancel, so now I have it by itself and on the top. So V2 equals T2 times V1 divided by T1. I've solved in letter form. Now I can put my numbers in. I get 373 Kelvin times 2.25 cubic decimeters divided by the initial temperature, which was 298 Kelvin. The kelvins are on top of each other, so therefore they cancel out. I grab my calculator of science, and I do all the work on top. 373 times 2.25 equals, divided by 298. And I get 2.8162 and a whole bunch of calculator junk. So I ask myself, how many of these numbers do I have to keep? So that's my significant figures. So I go over here and I see 1, 2, 3, 1, 2, 3. There's 3 significant figures in each of these numbers. So I'm going to keep 3 significant figures here. Keep the 2, keep the 8, keep the 1. The 6 rounds the 1 to a 2. So my number is 2.82. 2.82 decimeters cubed. That's the label that's left. That's the label my answer gives. And then I ask myself, does this make sense? What did this do? I had an initial temperature and the temperature increased. So if the temperature increased, my volume increased. 2.25, 2.28, it increased. Yay! That makes sense. I did the math right. Woo! All right, then you do the rest. 5 through 7. Finish. This is what I want to see. Variable list, equation in variable form, solved in variable form, numbers, units cancel, answer, box your answer. That is how we solve problems in science. So complete 5 through 7 on your own. You can check your work against my work. It'll be posted in Schoology. Okay, so we've been having so much fun talking about these variables. We looked at Boyle's and what Boyle told us about pressure and volume. We looked at Charles and what Charles told us about volume and temperature. So the next step would be the next person who came in said, what about all of these three things together? Let's combine them. We'll combine these systems. And what in the world can I learn by combining the gas laws? Combine gas laws? What? Boyle's plus Charles's law are just called the combined gas law. So what does this tell me? It says that pressure and volume are directly related. We knew that. They're on the same side. They're on the same side of the equal sign. They are indirectly related. As pressure goes up, volume goes down, but they are directly related to temperature. So if I put them all on the same side of the equal sign, it looks like this, right? So pressure and volume, as one goes up, the other goes down, and temperature, as the temperature increased, we studied volume. So if volume goes down, the temperature goes down. Okay, cool. All right. So this is how they would set up, but there's other stuff here. We don't know what the stuff is, so the only way that we really can study gases is to keep them in this proportion where there is some initial and some final. So P1 V1 over T1 is going to be P2 V2 over T2, and this proportionality is called the combined gas law. And we're going to use it to solve problems. So I am going to look at your worksheet in your packet called Boyle's Charles Combined Worksheet. This worksheet is going to ask of you to identify which of the Boyles, the Charles, or the combined you should use to solve a problem. The only way we can do that is by writing the variable list and identifying what they've given us and then deciding what do we actually need in order to solve the problem. Right, so let's look. What is the new volume? Oh, volume, question mark. It's a new volume, so it's the second volume. What is the volume of a gas? Okay, at 25 degrees Celsius, oh, this is the temperature. If it occupies 50.2 cubic, oh, this is the volume. There's the volume. Oh, time out. Let me just do this. This is a volume, and this is a what is the new volume of a gas at 25 degrees Celsius if it occupies 50 cubic centimeters at negative 53 degrees Celsius? All right, I've got a volume, a temperature, and a volume and a temperature. Do I have an equation that just talks about volume, temperature, and volume and temperature? Volume, temperature, volume, temperature. Hey, it's a Charles equation. All right, so let's make the equations list. V1, T1, V2, T2. So volume 1, what is the new volume? Well, I don't know. What was the old volume? Oh, it occupied 50.2. Okay. 50.2 cubic centimeters at negative 53 degrees Celsius. If, what's the new volume? I don't know. What's the new temperature? Oh, 25. Let's look at these units. So far, I've just been telling you who cares? Keep them the same. Cubic centimeters. New volume will be in cubic centimeters. Rock on. But I have this Celsius, right? This is the standard unit of temperature we've been working with, Celsius. So here's a negative 53 and then a 25. What will happen in my equation if I go V1 T1 equals V2 T2? So like, don't write this down. Let's just look at what happens. I'm gonna go to my worksheet, my science notebook. V1 T1 equals V2 T2. And if I put these numbers in, okay, volume was 50.2 cubic centimeters, and the initial temperature was, time out. What's the new volume of a gas if it occupied, so technically I called these V1. It doesn't matter as long as they're together. So I have negative 53 degrees Celsius equals, what's the new volume? Okay, I don't know, V2 over T2. And I know I told you to solve these in equation form, but just look at the problem we have here. This negative sign, if I cross multiply these up, I get 50.2 cubic centimeters times 25 degrees Celsius equals negative 53 degrees Celsius times V2. I get a negative volume. Like, it doesn't even make sense. It disappeared. Like, I have a black hole. Like, how can I have negative volume? So there's an issue. Celsius system, there's an issue with this negative sign. The Celsius scale, the centigrade scale, goes from very, very negative values over here, negative Celsius, negative degrees Fahrenheit, all the way up here to positive degrees Celsius and positive degrees Fahrenheit for Fahrenheit and Celsius, right? So super awesome and all, except we can't use negative values in equations like this because we can't have negative numbers. So remember we talked about what is temperature? Temperature is just a measurement of the motion of these particles. So that's what we're measuring, right? We're measuring motion. Motion of particles. And their motion is a relationship to their energy. So we're just going to put energy. If you want to know how these things are related, take physics with me next year and we'll talk about this. So the motion of the particles is the measurement of their energy, and we have given that a scale value in Celsius and Fahrenheit. Well, this dude, Lord Kelvin, came along and said, if you are measuring the motion of particles, then there should be some point 0 where there is no motion of particles. That should be 0. So on his scale, on the Kelvin scale, what he did was he measured the motion of particles, and he started over here with gases, right? So we had gases, gas, particle, gas, particle, gas, particle. Well, as soon as he slowed the gas particles down and they stopped moving so fast, they started to stick together, and we got a liquid. Well, and liquids they don't behave like gases, blah, blah, blah. So what he did was he took the data from when it was a gas, right? And he extrapolated, meaning he predicted using math what the motion would have to be in order for it to be 0. So we have never actually observed particles in substances that can be at 0 Kelvin, no motion. We've gotten really, 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 really close, but we've never actually done it because it's theoretical, like 0 motion. So Lord Kelvin came up with this concept. We call this the absolute temperature scale because on it there are no negative numbers. And because there's no negative numbers, it's the perfect system for us to work with because we'll never have any negative numbers in our equations. So we just need to know how to convert between these scales. So mostly we just want to know, how do we go from degrees Celsius into the Kelvin? No degree, it's just the letter K. And on the back of your periodic table, it tells you right here. To go from Celsius to Kelvin, you just add 273 to the degrees Celsius. That takes you to Kelvin. So let's go back to our worksheet. In the worksheet, all I need to do is add 273 to this, and it turns those numbers into Kelvin. So negative 53 plus 273 is 220. 25 plus 273 is 298. And I can now enter those into this equation and solve for phi2. All right, so that is your assignment. This is your homework. Homework for Monday. Note, due Tuesday when I will be back. We will work through these on the board, and the solutions. I will post the solutions. I'm not going to post the solutions until I come back, though I want you to work through these on your own. So 1 through 5. I'm step 1, write the variable list. Step 2, identify the pairs of data. It doesn't matter which one's 1. It doesn't matter which one's 2. Identify the pairs. Write the equation in variable form. Solve in variable form. And make sure that your units make sense. The only time we have an issue is with Celsius. Make sure you convert it to Kelvin. All right, so we've talked about Boyle, we talked about Charles, and we talked about what happens if we combine the Boyle and Charles laws and we get the combined gas law. So you should have your Boyle's paper filled out by the end of class, or if it's not, by Tuesday, the Charles law worksheet, 5, 6, 7, and your homework, Boyle's, Charles combined, and your test is still on Thursday. Test on Thursday. So when I get back on Tuesday, we'll talk about ideal gas law and the diffusion of gases, how gases actually move in space. All right. Have a fantastic day, guys. I will see you in class tomorrow.